All right, in this set of notes, we're going to start to look at what are called circuit charts. So let me give you just a quick overview. So what I like to do when I analyze circuits is I like to have my original circuit written up here in the top left, and I like to draw my little, I'll call them sub-circuits down here when I'm starting to do my equivalent resistance and combining resistors two at a time until I get down to the bottom, and I know that I'm done when I have one resistor and one battery in my circuit. And then in the middle here, so far, this has been blank for us. Well, today it's not going to be blank anymore. This is where we're going to do our circuit chart. And when we do our circuit chart, it allows us to find answers to small little questions that there'd be no other way for us to do that. So I'm going to A, model that a little bit over the next couple of examples, and B, I picked a really simple example here that I'm going to use tonight to explain to you how these components kind of function together and how a circuit really works by making some sort of analogy. So just follow with me for a little bit, and I think it'll kind of make sense. All right, this is a very simple series circuit. So the math is really easy, getting the answers is really easy, but that's not the point. The point is to learn the process. So when we get to a fancier circuit that's not so easy to analyze, we'll have some skills to do that. All right, so I'm just going to pretend that this is my kitchen. Okay, so these numbers are not realistic at all, and my kitchen is really an AC circuit, and this is really a DC circuit, but oh well, we're going to go with it. So if this was my kitchen, when you encounter a resistor is something that slows down the electron flow, and you could think of it like an appliance in your kitchen. So I'm going to call this the toaster. So this might be my toaster. This one might be my coffee pot. I'll call it CP because I'm out of room coffee pot. And we'll call this one toaster oven, like a toaster oven in my kitchen. So when you plug things in, they function as resistors. The energy source in my circuit is going to be the battery. And you can see that my battery here is 24 volts. And you can see that the electrons, remember we're going to pretend they come out of the positive side of the battery, so they're going to be going this way. But before I can analyze this circuit, I have to go over here and I have to draw what I call the sub-circuit. And so I'm trying to find my equivalent resistance. Well, if my electrons came out of the battery, they would be marching around and they would go through the toaster, then they'd go through the coffee pot, then they'd go through the toaster oven, and they'd be back to the battery. And they had no choices along the way. No choices, no branching, no different paths. That means that all three of these things are in series. And if they are in series, I'm going to combine them together like this. So I'm going to draw a little circuit over here. And I'm going to put my battery back in, which is 24 volts. So 24 volts. And resistors in series, we just add them up. So I have 4, 5, 6, and 6 is 12. And I can put this resistor anywhere that I want it. So the REQ is 12. All right, so I'm really done here because I have one resistor and one battery. And so this now is the new step. All right, so the new step is what do you do when you're done? So when you're done, you are going to use or apply the equations Veer and PIV. So really Ohm's law, V equals IR, and power equals current times voltage. All right, so we know that we have a circuit that's 24 volts. We know the equivalent resistance is 12. So this kind of like becomes an REQ. So I now can learn the value for the current coming out of the battery. So the current coming out of the battery is obviously 2 amps. And then I can go over here and I can say that the current now is 2 amps. I have a 24 volt battery. And I can now calculate the power that this whole circuit is going to use when I have these three appliances plugged in my kitchen. And so my power is going to be 48 watts. All right, so one more time. Every time you have a circuit, you find your equivalent resistance, and then you do Veer and PIV, and you always want to know the current coming out of the battery, and you always want to know the power used by the whole circuit. All right, so now we're going to insert the circuit chart. In a circuit chart, how I remember the headings of the circuit chart, it's going to be the variables from Veer, V equals IR, backwards. So R, I, V, so that's Veer backwards, and then P. So you can see that if I look at it like this, I have Veer, and if I look at it like this, that's where PIV comes from, P equals IV. So that means that I can make now a table, and there are 1, 2, 3 resistors, 3 things plugged in my kitchen. And so it doesn't matter what order you list them, but let's we list all of these original resistors in the chart, in the circuit chart. And then I'm going to make a row for each value like this. And I'm going to make a column for each of these variables. But then I'm going to make one more box down here. That's where this goes. That means that my circuit, when I have everything plugged in, is going to draw 48 watts of power. And so I can use that answer to check my work. When I'm all done here with my circuit chart, if I add up all the power values, they should add up to 48. And if they add up to 48, that's going to tell me or let me know that my work is most likely correct. All right, so completing the circuit chart in this problem is going to be pretty easy, but in future problems, it can get a little tricky sometimes. So what you do is, this is called the calculate, let me write that down, calculate and carry back method. Calculate and carry back method of analyzing a circuit. So when they say calculate, they mean use Veer. And then take your answer and carry it back to the picture before this one. So let me say that again. In this picture, we took this picture and we calculated. We got an answer. We take the answer and we carry it back to the picture that's before this one, because we use this one to calculate, carry back. All right, so what did we carry back? We learned that the current coming out of the battery was 2 amps. We just learned that the current coming out of the battery was 2 amps. So like now we know how fast the marching ants are going. So those marching ants now are going to be going at a speed of 2 coulombs per second, because that's what an amp is. And those are marching electrons go around, and they're going to have to go through the toaster. They're going to have to go through the coffee pot. They're going to go through the toaster oven, and then they're going to be back here. All right. Well, how does that relate to the circuit chart, and how does that relate to my story? All right. So right now, I want to change the story slightly, and I want you to pretend that the current is the marching ants, and you are the lead marching ant. So you're going to set the speed 2 amps, and you're going to be carrying the energy, and the energy is 24 volts. So I want you to picture that you're the lead marching ant, and you have 24 sticks of dynamite in your pocket, 24 sticks of dynamite. And instead of these being resistors, I want you to picture them being mountains, all right? And so when you hit a resistor that has resistance, you're going to have to spend some of your sticks of dynamite to blow up that mountain and get it out of your way so the marching ants can keep on going. So let's go with this story here for a minute. Okay, so here we go. You're the lead marching ant. You got 24 sticks of dynamite. So march, 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 march. Oh, you got right here. By the way, you are still carrying 24 volts. You are still carrying 24 sticks of dynamite, 24 volts. You are now going to have to spend some of them because you just encountered a mountain that is 4 ohms big. So I'm going to write in my chart, I was marching with a current of 2 when I encountered a mountain of 4 ohms. There's the resistance of 4. So how many sticks of dynamite is it going to cost me to blow up this mountain? So I'm using VIR. V equals I times R. So 4 times 2 is 8. It's going to cost you 8 sticks of dynamite. So you take out 8 sticks of dynamite, you light them, you blow up the mountain. And okay, so now you walk. Now you and your marching ants can cross this. But by the way, you just spent 8 sticks of dynamite. So how many do you have left? 24 minus 8, that'd be 16. You have 16 volts. All right, you have 16 sticks of dynamite left. So now you're march, 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 march. And here you are. Here you are. You just encountered a resistor of 2. You were still marching with a current of 2. But you know what? This mountain's not as big. This resistance is not as big as this one. It's only a 2. It's only a 2. So how much voltage, how many sticks of dynamite are you going to have to spend to get through this one? 2 times 2 is 4. You're only going to have to spend half as much because it's a smaller resistor. So you take 4 sticks of dynamite out of your pocket and then you blow up this mountain. And by the way, so you had 16 when you approached this. You took 4 out of your pocket, so now you only have 12 left. 12 sticks of dynamite, but you and the marching ants keep on going. You keep going. And here you are, 12 sticks of dynamite, 12 volts. But now you encounter a mountain of 6 ohms. That's a pretty big mountain. It's going to cost you a lot of sticks of dynamite. So you were marching with a current of 2. You encountered a 6. 6 times 2 is 12. It's going to cost you 12 sticks of dynamite. But you got 12 sticks of dynamite in your pocket. So you take them all out. You blow up this mountain. And then you, by the way, when you get over here, you and your ants, you have 0 sticks of dynamite left. So you have 0 volts. And so then you keep on going over here. You keep on going over here. And when you cross the battery, that chemical reaction takes place again. And you went from 0 volts. And when you cross the battery, you get like 24 more volts of energy. You get 24 more sticks of dynamite, and then you can march around the circuit again. And that's what happens in a DC circuit. As you keep going around, you keep going around, you keep going around. And voltage is your energy source. So you end up having to spend your energy source to go through resistors, to heat up appliances. So we're not blowing up mountains. We are heating the toaster. We are heating the coffee pot. We are heating the toaster oven. And they can have different amounts of resistance. And this is how much voltage I have to spend to heat those appliances. Let's go a step further now, though. Let's now look at our circuit chart. And now I'm going to start to think of P equals I times V. So how much power am I using? So 2 times 8 is 16. 2 times 4 is 8. 2 times 12 is 24. Let's add these all up. So that's 24 plus 24. That's 48 watts. So first of all, the numbers add up. So that tells me, check, that's good, that our answers are probably correct. And do you remember we already learned that you get charged for how many watts of energy that you use? Technically, we had to change it into kilowatts, and then we had to multiply it by like the hours that we used those appliances. But this is what you get charged for, and this is what makes sense of all of that. So this is the process that we want to use when we have complex circuits. In real life, in your house, the circuits are very complex. They're not a simple circuit like this one, but I kind of like the analogy of the story that goes along with this. So use this just kind of as a concept, but also use it as an idea of how to organize your work on your paper, okay? Always our big circuit, our sub-circuits, VIR and PIV, our circuit chart, talk to yourself, make a story up, and see if everything adds up to the power. All right, I'll stop this video, and then we're going to go on to the next example in the next video.